I will talk a little bit again about kinetic theory. So forgive me for that. So here's a brief outline of the talk. I will start trying to explain to you the flow configuration that I'm interested in. Then I will try to phrase the boundary value problem, because I will integrate differential equations. I will show you some results that are qualitatively and quantitatively in agreement with literature. And then I will talk a little bit about the supported flow, or at least the type of flow that I call supported flow, and then some conclusions. Okay, so here's the flow configuration. It's pretty simple if you want. It's a steady and fully developed flow on an incline, no sidewalls, okay? Think the bed is rigid, and it's bumpy because you have semi-spheres glued at the base. Particles are all the same size, okay, and all the same density. So I'm using the particle density, the particle diameter, and the gravitational acceleration to make everything dimensionless. Particle volume fraction is new. I will use kinetic theory, so I will use a constant coefficient of restitution that I call E. And then U is the particle velocity in the direction parallel to the bed. Okay, so pretty simple. It's a free surface flow. Okay, although okay, so capital H is the depth of the flow, whatever it means. So here are the balances that I'm going to use. So two are the momentum balances along x and y, okay, in the flow direction and in the direction perpendicular to the bed. I'm ignoring, of course, the other direction. Then I need an additional balance, which is the fluctuating energy balance, because I'm using kinetic theory, so I'm using the granular temperature concept. And this energy balance in this steady, simple situation means that you have diffusion of energy, you have production of energy due to the shear stress, and then you have collisional dissipation due to the fact that collisions are inelastic. Of course, I'm not sure it's clear, but if you ignore the diffusion term, then you get out with a balance between production and dissipation, and this is where the mu areology comes from in the context of kinetic theory. So if you have diffusion instead, you have a non-local term, okay? Then I need constitutive relations. I'm using the constitutive relations from kinetic theory. So, okay, I have the equation of state for the pressure, quite simple. Equation of state, a constitutive relation for the collisional shear stress, for the dissipation rate. This is the main difference between the classic kinetic theory and the extended kinetic theory, because when the flow is very dense, that means more than 50% in concentration, the molecular chaos assumption is not anymore valid. But you can take, as a first approximation, into account this effect by decreasing the dissipation rate, okay? And by decreasing the dissipation rate, I mean that you have to introduce an additional length scale, which is this kind of measure of the size of a cluster. Well, you can introduce a phenomenological law for this additional length scale, which comes from a balance between the shear rate and the fluctuating velocities. So one is trying to build up the clusters, the other one is trying to destroy the clusters. This is the idea. And there is C, which is a material parameter somehow, okay, about the unit. And then you have a constitutive relation for the energy flux. Depends on the gradient of the temperature and the gradient of the volume fraction. So this is pretty much well known, except maybe for the correlation length, capital L. The function Fi that are there may be quite complicated, but all of them are just function of the concentration and of the coefficient of restitution, okay? So we can just disregard the details. So we have some equations involving the derivative of terms, because u prime means, for instance, the derivative of u with respect to the y direction. So we can phrase the differential problem like this, using the balances, momentum balances and energy balance, and the constitutive relation of kinetic theory. So it's going to be 1, 2, 3, 6 differential equations. Okay, I added this guy, in order to control something in the flow. And what I control, apart from setting the inclination of the bed, is what has been called the mass hold-up per unit area. Okay, which is nothing else that the average concentration times the depth of the flow. So I have this additional differential equation in order to fix this additional boundary condition. Then I need boundary conditions. So here what I'm using, at the top, I'm using the boundary conditions that comes from the idea that at the top you have a collisionless ballistic layer. Okay, I'm not entering details in that. Then I'm fixing the mass hold up. Okay, and at the bottom I'm using the boundary conditions that Richman have developed for a bumpy base. So I have a condition for the energy flux at the bottom, and I have a condition for the slip velocity at the bottom, because the grains are allowed to slip. And then, of course, I have this trivial boundary condition. So I have 7 boundary conditions, 6 differential equations, and the additional boundary conditions is needed in order to have a definition for capital H. Okay, so now the problem is closed. I can easily solve it easily using a MATLAB standard library. I mean easily because the trouble is to have a starting solution which works. That's the only problem. But once you got that, then it's easy. And of course, if I have a solution, that means that I have distribution of all these guys in the flow. So for instance, from the integration of the velocity and the concentration, I can have the flow rate. So I can have whatever I want, profiles, global quantities. So here I'm plotting the results in terms of mass flow rate as a function of the mass hold up at a certain angle of inclination. So in real experiments, okay, or numerical simulations or whatever you want, you can, I don't know, increases the mass hold up at a fixed flow rate, or you can fix the hold up and increases the flow rate. Okay, this is the idea. So these results show some interesting features. First feature, there is a branch here that I call diffuse flows, and I will try to explain later what is a diffuse flow for me. Then there is another branch, which is a dense flow, okay, where the flow is rather dense all over the depth. And then there is this additional branch, which is quite weird. And here I'm a little bit cheating, because in order to have this point here, I have to give up in controlling the hold up, and I have to move in controlling the concentration at the bottom, which is not easy to control in a real experiment, okay? So in a real experiment, what you would have probably is you follow this branch up to here, then you increase the mass hold up, and you probably jump here somehow. Or if you go down with the hold up, you will follow this branch up to here, and then you probably jump to this other branch here, okay? So this is the idea. It's kind of hysteretic behavior, if you like. So this branch is likely not to be attainable in experimental in simulations. And also here, I've plotted the results of Pullican on an inclined flow. So as you can see, for an angle of 26 degrees. And here I'm using a bumpiness, which is a measure of how the grains glued at the walls are separated, okay, which is pretty low, pretty high. That means that the bed is very bumpy. So if it's very bumpy, that means that the slip velocity is quite low, okay. But so actually it's not low enough. So probably the bumpiness in Pullican's experiments is even higher for some reason. But still, as you can see, the qualitative trend is well reproduced from kinetic theory, okay? So one thing that I want to show you, so this kind of, having two branches, so for instance, for the same mass flow rate, you can have, in this case, up to 3 solutions, okay? Has been seen before. In 1990, there's this nice paper by Johnson and co-workers, And they were, okay, there are some differences because they were performing experiments with glass spheres on a flat bed, not bumpy. But still, they were able to see these two branches starting with different initial conditions. So more energetic, okay, this branch, more dense, this branch. And they were observing this jump from one to the other. So the qualitatively, we seem to be all right. So here I'm trying to explain what I intend for dense, diffuse, and supportive flow. So here are profiles of concentration, volume fraction, and velocity. Okay. So in the case of diffuse flow, as you can see, there is not a plateau anywhere in the flow. So if you have a plateau, that means that there the algebraic balance between energy production and dissipation holds. Okay, and that's why the concentration is rather constant, because the stress ratio is rather constant if you don't have sidewalls. Okay, so a diffuse flow is one that is entirely influenced by the boundaries. Instead, a supportive flow is one where you have a core, and then you can distinguish a basal layer where you have a lower concentration. So you can have, it's a flow supported by a basal collisional kind of dilute layer, if you like, even though it's not so dilute. And then you have a dense flow, so it's entirely dense, even at the bottom, okay, except for close to the free surface, of course, where you have a decrease in the volume fraction. So qualitatively, this is how I define the three different flows. And this is for the flow velocity. So then we have looked at the effect of the bumpiness. So we have reduced the bumpiness. That means that we have made the hemispheres glued at the walls closer. So if you reduce the bumpiness, this is the effect. It's like, you know, you have the curves that is a little bit stretched out. So this branch moves in this direction, and the curves, the relation becomes monotonic. So that means that you can attain supported flows even in experiments and in numerical simulations, probably, just by increasing the mass hold up. Okay. And here a closer look at the supportive flow regime. In particular, these plots refer to this case here. Okay. And so this is a plot for the velocity in the direction parallel to the bed. For the concentration, so here it's pretty clear. You have a dense core supported by definitely more dilute basal layer. And then this is the profile for the granular temperature. So what you see is seems that the core is almost cold, okay, while the bottom is much hotter, okay. And these features have been seen in numerical simulations by Nicolas Taberlet and co-workers in 2007, okay. And qualitatively, these are the same. I didn't try to fit the parameters in order to reproduce also quantitatively the profiles. Something that I can do in the future. And I think that's pretty much all. And these are the conclusions of the talk. So, pretty fast.
Only one question is your curiosity. Have you seen, again, what is the effect of this new length scale in your calculation? Let's assume that you forget the contribution of this term.
You cannot have that the concentration in the dense core is increasing when you decrease the angle of inclination.
That's the wrong way.
You would have a constant, I mean, in the dense limit, kinetic theory would predict a constant concentration if you change in the stress ratio. That means that if you change the angle, the concentration is going to be the same.
Okay.
Well, it's very different from what you got from numerical simulations. Am I right, Michel?
Well, sure. And there's also another thing, which is the flows at 0 degrees of angle.
Yes, you're right. Yeah. But I'm not going
Well, yeah,
in any case close to that angle. Yeah, but I agree with you.
nonetheless, it's useful for the practitioners to know about that.
You think I should make a comment about it? So the problem with this length scale, here for those who are not familiar with that, we are talking about this guy. This guy, okay? So here, the problem is there is this capital G function in here, and the capital G function is a function of the radial distribution function. So in this expression, the correlation length diverges at the concentration at which a shear rigidity develops. So that means that when you take the ratio S over P, okay, and you plot it against nu, against the concentration, you would have a flow also for this ratio equal to 0. So one problem of the theory is that you are not predicting the stopping angle, right? Something like that. But of course, you can make modification for that, right? Phenomenological modification.
I'm surprised that in the dense profile that you show us, you do not predict the Bagnall profile. It's quite linear, your velocity profile.
You're a good observer. I was cheating because I'm lazy. Sorry. These results refer to the case with sidewalls. So it was 30 diameter wide. So I didn't want to replot the data because in the paper in 2012 we performed the numerical integrations either with or without sidewalls. So these plots refer to the sidewalls effect. That's why you don't have a Baghdadi profile.
Well, for shallow flows, it's known that you, observationally and from simulations, you do get a linear profile. So can your theory produce that?
The linear profile for the velocity, you mean?
Yeah.
Well,
And it's a bit of a mystery, really, how you can get this finite
Well,
shear rate at the top.
I see, but let me see. So if it's shallow diffuse or shallow dense?
Dense. Generally, once you start getting close to where it won't flow, the velocity profile's
So
linear or even convex.
I'm not sure. I mean, depends. If it's dense and it's supported, then maybe there is a strong influence of this basal layer. And if there is a strong influence of the basal layer, here the velocity is going pretty much linear. So
Change the computer.
It's really normally it's dense all the way down, and it's just somehow the grains are more mobile. It's
with sidewalls or
without sidewalls.
Without sidewalls. Depends on boundary condition at the bottom probably also. So it's a flat bed or bumpy bed.
I have a question. When you say that those states are stable or unstable,
Yeah.
so if I understand correctly, you solve for the steady state solution. Can you solve for the whole dynamical equations with the time derivative and look?
Yeah, with a PhD student, yeah.
Okay.
Yeah, I mean, yes, of course, in the future I would like to do that. I would like also to have a 2D solver, but I have to have time for that, yes. And I think that the steady and fluid bed flow is already a mess. So.
Any more questions? So let's thank the speaker and all the speakers.